The universe is going to end. It won't happen for billions of years, but there is no way out. Figuring out how it will end is the challenge of astrophysicists around the world. They're pointing high-tech equipment out toward the heavens to unlock the secret of our fate. The possibilities are frightening. In one scenario, gravity pulls the universe back into itself, similar to air being let out of an inflated balloon. The universe goes back to its original size. This is the Big Crunch.
That'd be the end of the universe, and a big fireball, as all the matter collapses onto itself. That'd be pretty dramatic.
Then there's the Big Chill. The universe expands until the nuclear furnaces that power all the stars burn out. The universe grows cold and dies.
A second possibility is actually kind of sad. The universe will continue to expand forever, and it will just grow into an increasingly cold and lonely place as the expansion removes our nearest neighbors from us, and we just end up a single isolated community of stars and galaxies.
Then again, there could be a much more spectacular end in which everything is ripped to shreds, down to the last atom. Think of it like a balloon that is filled with too much air. It pops.
It's much more dramatic than the Big Chill, and just as fateful as the Big Crunch. The universe continues to expand, but at an ever-quickening pace. And in fact, the pace is so great that even the space-time fabric cannot hold the universe together.
However the end comes, it will be a dramatic conclusion. To understand how it all could end, scientists turn to how it began. The mystery starts to be solved here, at the Mount Wilson Observatory overlooking Pasadena, California. In 1929, while looking through what was then the world's largest telescope, Edwin Hubble makes a strange discovery. The universe is expanding.
Hubble's discovery led to a whole new picture of the universe, that it was a dynamic environment and that it evolved. It changed in time, and that's different from pictures that people had of cosmology previous to that.
Before Hubble, scientists said that the universe was static and unchanging. Hubble's discovery that the universe is expanding meant it had a starting point, a beginning.
That brought the idea forward that, hey, what if we ran the film backwards in time and found the point at which that began?
The Big Bang. That fraction of a second when the universe and everything in it exploded into existence from a point smaller than an atom.
One common misconception about the Big Bang is that we can identify a point in space where the Big Bang occurred. But in fact, it's more appropriate to think of the Big Bang as a simultaneous creation everywhere of space, which is then continuing to expand to the present day.
Scientists theorize that at the moment of the Big Bang, the first small particles of matter called quarks were produced. They collided to form the building blocks of the universe. These floated in a thick fog of hot plasma for about 400,000 years. Gravity, also created at the Big Bang, drew the particles together, eventually creating the first stars and lighting up the cosmos.
The theory of the Big Bang is a very solid theory. What happened at the moment of the Big Bang is still something we're working on. We don't really understand.
If the universe has been expanding since the Big Bang, scientists must consider that it will stop expanding at some point. The question is, how? The most obvious answer involves gravity. What goes up must come down. Stars and galaxies and everything else might reverse direction. The universe would collapse in what some scientists call a big crunch.
Take the top and then see the other handle and just jerk them apart.
A model rocket offers clues to how the big crunch would work. The rocket is like the universe expanding into space out of the Big Bang. An initial bang allows the rocket to overcome the pull of gravity.
5, 4, 3, 2, 1.
Eventually, when the fuel is exhausted, the rocket coasts a few feet higher, stops, and is pulled back to Earth. This is what would happen with a big crunch. The entire universe is essentially pulled back to its launch pad.
The universe itself has its own momentum, its own energy. It's moving outward. But eventually, there's a point where possibly the universe will stop that moving outward, just like the rocket that we saw, and have to fall back in upon itself and collapse again under the force of its own gravity.
In this scenario, the universe could return to its original state just before the Big Bang, setting the stage for a perpetual seesaw of creation and destruction. The Big Crunch theory moved to a scientific back burner. Cosmologists figured out that there must be some form of energy that keeps the universe from collapsing. The existence of such a force leads to new theories about what the universe is made of and how it might end. And evidence about how this might play out is found in some of the most powerful and mysterious phenomena in the cosmos: black holes. Predicting how the universe will end involves some of the most advanced technology known to man. On a remote volcano on the island of Hawaii, astronomers are monitoring a battle in space that is shaping the fate of the universe. At an elevation of nearly 14,000 feet, the Keck telescopes bring astronomers from all over the world nearer to space for a clearer view of the cosmos. They come here because the telescopes work best far away from city lights and as high as possible above Earth's polluted air. Harsh conditions make it difficult to work here, but for scientists in pursuit of the great mysteries above, it's paradise.
So this is a remarkable location, but of course the air is very thin, it's extremely hard to work here, but these telescopes are amazingly powerful. But we're ambitious astronomers. We don't just stop looking at easy objects. We try hard to look at the very faintest objects so we can understand the extremities of the universe.
Here, astronomers like Richard Ellis are working on a problem that has been all-consuming for cosmologists since Edwin Hubble. They know the universe is expanding, but what they don't know is how fast. It will be difficult to predict exactly how the universe will end until they solve this mystery. The answers lie in the past.
Now, what I did the focus on was a V equals 12.
There it is, yeah. Okay, that's the right star.
Get a better focus now. That was worth doing.
An astronomer like myself uses a ground-based telescope as a time machine. We're looking back in time to study distant galaxies, seen as they were a long, long time ago.
One of the distant galaxies that astronomers found revealed a powerful source of X-rays from something that they could not see. It was in the constellation Cygnus and emitted no light, but something was there. Whatever was emitting these X-rays had a mass about 7 times that of Earth's sun. There wasn't a name for it, so they called it a black hole. Black holes offer scientists an analogy to how the Big Crunch theory works. When certain stars run out of fuel, they collapse in on themselves into a smaller and far denser mass that attracts more and more matter, just like the Big Crunch. The gravitational pull is so powerful that anything that falls near a black hole will be forever trapped. Not even light can escape. It's a mind-boggling concept that something invisible is detectable and offers a view to our ultimate fate.
This black tarp represents space, and space is relatively flat. But when you put a massive object into space, it curves it. This is a penny, and notice how it comes into a really beautiful circular orbit. Basically, the black hole trapped it into an orbit around itself. And that orbit becomes very circular as it gets closer. And now the penny will eventually disappear, go inside the black hole.
Earth's sun warps space similarly to a black hole, only it's a cosmic wimp by comparison. The gravitational pull of our sun is much weaker. Earth and all its nearby planets are trapped by the sun's pull, but it's so mild that it just stays in orbit without being sucked into the sun. The mass of a black hole can be 1,000,000 times the mass of the sun, or more, causing a huge warp in the space around it that consumes everything that comes near.
That black hole wraps space around itself. And so if material falls near it, it falls inside and gets trapped forever.
Black holes exist in isolated areas throughout the cosmos. A black hole's gravitational pull is a scaled-down version of the force that could cause the universe to collapse. That force is dark matter, and dark matter is what scientists often call cosmic glue.
Hi, Matthew. So let's do some cosmology here. Dark matter attracts other objects via its gravitational attraction. It's a positive force.
There's another force that opposes gravity, and that is dark energy.
Dark energy, we don't really understand what it is, but it's a negative repulsing effect that pushes galaxies away from each other.
The whirlpool in Richard Ellis's demonstration represents the gravitational force of dark matter. The green dye coming out of the syringe shows how the stuff of the universe collapses under the force of dark matter.
The presence of dark matter acts as the focus for the gas in the universe, bringing structure together. This is how the Milky Way developed as the universe expanded. Little things merging into big things, the positive, constructive force of gravity. Now, if this was the only force in the universe would stop expanding at some point in the future, and eventually the universe would start collapsing. Gravity would eventually halt the expansion, bring it back together in a big crunch.
Yet the universe continues to expand and isn't showing any signs of collapsing. This suggests the opposing force of dark energy could be stronger than dark matter. But it will take scientific detective work to find out. They look to one of the most violent forces in the universe for clues.
We're studying exploding stars to try to understand if they can tell us the rate at which the universe is expanding.
These are explosions at the end of the lives of stars, not unlike our sun. The fuel that these stars have in their centers is spent. The star collapses, the outer part expands, and the star becomes something called a white dwarf.
White dwarf stars sometimes have other stars orbiting nearby, a companion star. A massive explosion could happen if the companion star's debris falls onto the white dwarf, causing a spectacular fireworks display in the cosmos. Scientists consider exploding stars, or supernovae, like in these images captured by the Hubble telescope, to be reliable telltales of how fast the universe expands. Their brief and bright explosions allow scientists to track the universe's expansion and give them a way to measure its speed.
Essentially, they are white dwarf stars that become nuclear bombs. They explode with a certain brightness and a certain length of time. It takes a certain amount of time for that brightness to dissipate. They are essentially standard candles. Any one of these will look the same no matter where it is in the universe.
Astronomers measure the distance and speed of these exploding stars by measuring the amount of red light they emit. The faster the star moves away from us, the redder its light appears. The expansion rate of galaxies containing stars like supernovae can then be used to interpret how the rest of the universe is moving outward.
We know this because we can compare the velocities of galaxies with their distances.
These are the clues that lead astronomers to answer just how soon the universe will reverse direction and come back together in a big crunch. Or, this information might lead to an entirely different conclusion. Dr. Ellis is looking at clues at the Keck Observatory in Hawaii. While the telescope is on the top of a huge volcano, he's in a viewing room on another part of the island.
Hey, emission lines, Johan.
Oh, you see it?
In the red side, I think.
At the same time, Johan Richard is at the California Institute of Technology in Pasadena, California, evaluating the light from a distant galaxy that the Keck telescope captured in Hawaii. He's looking to see if any of the known elements coming from the galaxy are in the red spectrum and moving farther away.
We can interpret that as a velocity, as how much the galaxy is moving away from us. We can really interpret how the entire universe is behaving, is expanding.
Interpreting redshift